All right, we're going to finish up with our entropy and free energy section here. First, we're going to start off and talk about free energy and pressure. So, for dependence on pressure, delta H is not dependent. Remember, that's our enthalpy, or usually our heat, is not dependent on the pressure of the system, but delta S is. Why? Well, if you remember delta S, if you remember, is going to be entropy, which is a reflection of the randomness or the chaos, or in other words, how fast the particles can move. So if there's more pressure, they're not going to have as much freedom, so there's going to be less entropy, so there will be a dependence on that. Now, delta G is dependent on both delta H and delta S based on its equation. So it also is dependent on pressure. So we have to also have a little bit of a discussion on what that's going to look like. Now we can calculate the delta G of a substance at a pressure other than 1 atm, because if you remember, we've been doing a lot of the prime stuff, which is 1 atm and 25 degrees. Okay, so here is our equation for a pressure not at 1 atm. You've got, remember, delta G prime is still at the prime conditions. Then what you have is change in free energy at 1 atm. Delta G is the free energy at the new pressure. Okay, so it's kind of like G1 and G2, I guess you could think of it. R is the gas law constant. It's going to be the gas law constant since we're dealing with pressure. That's the 8.31 because it's got joules. T is always in Kelvin. Okay, so we can also determine the delta G for a reaction using the reaction quotient as well. Same Q that we were dealing with equilibrium. Again, R is the gas law constant, just like I said earlier. Here's the 8.314 joules over moles times Kelvin, as opposed to the 0.08206 liters times ATMs over moles Kelvin. Q is the reaction quotient in pressures or concentrations, either one. Okay, remember, our reaction quotient is simply going to be the ratio of the products over the reactants, and only taking into consideration gases and aqueous solutions. Okay, so for example, find the delta G for the following reaction at 25 degrees Celsius and with carbon monoxide at 5.0 atms and hydrogen at 3.0 atms. Okay, so you've got carbon monoxide and hydrogen reacting to form methyl alcohol. First, we got to find delta G prime. We do that by using the product and reactants values from the appendix, using our summation rules, or equation rather, where we have the sum of the products minus the sum of the reactants, and it's going to look like this. Then we calculate Q from the pressure values. So here's our values we found from the appendix. We plug and chug those. We get negative 29 kilojoules. We're going to have to get that to joules in order for the units to match when we use our R value. Okay, now to find Q, this is methyl alcohol is a liquid, so it's not going to count. So it's 1 over the two reactants. Hydrogen has a coefficient of 2, so that's why we're going to square it. So our Q is going to be 2.2 times 10 to the negative second. So now we can go ahead and find delta G. There's my equation. Okay, so we're solving for delta G. We've got our delta G prime, which we found up here. Remember, we just went by times 10 to the third to get to 2 joules. We've got temperature, and we've got the natural log of the pressure. So we can say at these new conditions, it was negative 38 kilojoules per mole. Once we got an answer, we went back from joules to kilojoules. You could have very well said joules per mole here. Give me this answer, and that would have been just fine. Okay? So since we had greater pressure here, you'll notice that the delta G value went up from standard conditions, or was more negative, so it would have been a larger because you had more pressure and more pushing those particles together. Okay? All right, so what does delta G mean? Well, delta G means the reaction lies to the right at equilibrium. Okay, so the system is mostly going to contain products. Okay, so it's using that available energy. It's going to have favored that we're going to be going this direction. Okay, all right, now we're going to talk about free energy and equilibrium. Now, equilibrium, this is just looking at different fractions and kind of where equilibrium occurs. So no matter how much of the reactants or products are initially mixed, at a given set of conditions, the equilibrium position, or K, will be the same. Okay, it's just in the given set of conditions is mostly temperatures and pressures that will dictate how much the collisions that are going to occur or not. So at equilibrium, and we've used this before when we were talking about finding boiling points and melting points, delta G is equal to 0 and Q is equal to K. Not brand new concepts, just kind of reminding ourselves of what that looks like. So what we can do here is kind of rearrange some of these equations to end up with another equation that shows a relationship between delta G prime and the K values, or the equilibrium position. So again, we can use this to our advantage. So just as a reminder, at delta G is equal to 0, neither the products nor the reactants are favored. Okay, K is equal to 1, right? It's a 1 over 1, it's an equal ratio, everything's even, we're good to go. Okay, for delta G prime being less than 0, the products are favored. K is greater than 1. And for delta G being greater than 0, the reactants are favored. K is less than 1. It's just trying to show you some of those relationships between the K's and the delta G's. Okay, so it's just kind of showing you again what some of those mean. All right, now if we look at another example, if we have our Haber process where we're generating ammonia, the delta G prime is going to be negative 33.3 kilojoules per mole. For each of the mixtures below at 25 degrees Celsius, we want to predict the direction to which the system will shift in order to reach equilibrium. Okay, so if we have a situation where pressure of the ammonia is, when they're all gases, so they're all going to count, 1.00 atms, 1.47 atms, 0.0100 atms. So we got to find Q. Okay, because we're trying to figure out where it's going to react to reach equilibrium. So the Q value is going to be 6.8 times 10 to the 5th. Okay, so that's our Q value. Now we go ahead and we plug that into our expression where we have delta G is equal to delta G. This is at a new pressure. So here's my delta G prime. Okay, here is my R. Here is my T, and here is my natural log of Q. So when I plug this in, all that work to say delta G is equal to 0, it's already at equilibrium, so there is no shift. Okay, there is no shift there. I know it's a lot of work to say nothing happens, but this one isn't going to be the case. All right, so here our Q value is 1. We do the same thing. Now we've got a delta G equal to negative 33.3 times 10 to the 3rd joules. Since still at standard states, meaning pressure is equal to 1 atm, okay, so since the delta G is negative, K is going to be greater than 1. We need to create more products, so it's going to shift to the right. And that's just going back to that slide where I talked about if delta G was negative, positive, or equal to 0, where it was going to be. Okay, so since it's negative, K is greater than 1, we need to create more products and we need to shift to the right in order to reach equilibrium. Okay, so hopefully we're getting this idea that there's really a whole lot of things that go on to fully examine or fully look at a system, any chemical system. Okay, now we got to talk about temperature dependence because we know that K's are temperature dependent. Okay, so here's a little bit of math in order to get to an equation that looks like this. Now, we may not recognize it, but we can look at this in the form of y equals mx plus b. Okay, so we've got our y equals mx plus b. So we're going to say a plot of the natural log of k versus 1 over t is linear. Again, where y is equal to the natural log of x. X is 1 over t, okay, and our slope then is going to be delta H prime over R. So it's just manipulating this equation. Let me write this above here, mx plus b. And then we've also identified our b over here is delta S prime over R. So it's just, you get something in that format and you can analyze it graphically, which may not be exciting to you, but a lot of people did a lot of math to figure it out. Okay, last but not least, we got free energy and work. It's kind of this random point that we got to make. Work, we can calculate the maximum amount of work that can be done by any process. Most of the time when we talk about chemistry, we talk about work being done by gas particles and pressure being exerted on something. And the work, the maximum amount of work is also equal to delta G. So if delta G is positive, then W is the amount of work expended to make a process occur. Okay, because remember, if delta G is negative, that's when things are good. So impossible to achieve maximum work because of the amount of wasted energy. So this is a little bit on that high end of ideas, just to mention it so that we've heard it. Okay, so that is the end of free energy, and we'll go from there.